Thank you, Dr. Shi. Good afternoon, ladies and gentlemen. My name is Jialuo, and I'm the Assistant Director of the National UTC Center of Tridolite based in Washington State University. Today, I would like to talk about the chemical impacts of magnesium chloride on ordinary Portland cement and high-volume fly ash concrete. So here's a table of contents. I will start with the introduction of the background, discuss the experiments that we did in our study, and then I will share some interesting results and findings with you. And finally, I will make a few conclusions. So, de-icing versus deterioration. The picture on the left-hand side shows how people usually spray the de-icing salt on the surface of roadways for ice melting. And the phase diagram of three commonly used chloride-based de-icing salts show that the freezing temperature of magnesium chloride has the lowest value at the same concentration compared with chloride, calcium chloride, and sodium chloride, which indicates it has the highest efficiency in ice melting. However, the application of magnesium chloride can chemically and physically attack the concrete infrastructure, which cause the premature deterioration at the joint and concrete pavement surface, and subsequently result in the rebar corrosion. Our previous study found that when concrete is immersed in magnesium chloride solution along with freeze-thaw cycles and wet-dry cycles, there will be severe deterioration inside the concrete, while we can hardly see any visual and obvious distress on the outer surface, which means that it's a complex mechanism of magnesium chloride for deterring the concrete. In that way, we are trying to separate the mechanism of chemical attack and physical attack apart. So in our study, we are going to focus on the chemical attack. Compared with calcium chloride and sodium chloride, there are multiple chemical reactions between magnesium chloride and concrete. Here are the first two primary reactions that magnesium chloride can react with calcium hydroxide and CSH gel, which are the two main components of concrete, and produce magnesium hydroxide, MSH gel, along with calcium chloride. Then, the produced magnesium hydroxide will further react with the magnesium chloride to produce the magnesium oxychloride phase. And the produced calcium chloride can further react with the calcium hydroxide in the concrete to produce the calcium oxychloride, which is an expensive and destructive phase, and it is one of the main reasons how concrete is deteriorated by the application of calcium chloride. Well, don't forget that magnesium chloride can also react with the monosulfate in concrete and produce phytyl salt and magnesium sulfate, which is also known as the chloride binding reaction. So in our study, we prepared two groups of cylindrical mortar sample, which are control samples using purely using the type 1-2 Portland cement, and the high volume fly ash sample using both the type 1-2 Portland cement and class C fly ash. The water to binder ratio of control samples is 0.4, while that of high volume fly ash sample is 0.3. The replacement level of fly ash is 60% by weight of the total binder. The binder to sand mass ratio is fixed at 1 to 1.5. So after 28-day curing under 23 degrees Celsius and the relative humidity of 95%, all the mortar samples will be immersed in the magnesium chloride solution with a concentration of 11% by weight. The emission period will be 14-day, 28-day, and 56-day. So after the immersion period, we will take out the sample to do the test of compressive strength, splitting tensile strength, and gas permeability for monitoring the change of mechanical properties and durability of samples. In addition, we conducted the X-ray diffraction analysis, thermogravimetric analysis, and SEM-EDX to further characterize the change of microstructure and the chemical reaction products in the samples. So let's first start with the compressive strength result. As you can see here, for control samples, after 56-day immersion, there's a slight reduction of 2%, while for high volume fly ash samples, there's an increment of 19% after 56-day immersion. In terms of splitting tensile strength, we may find that both control and high volume fly ash concrete mortar samples have an increment of 136.5% and 47% respectively after 56-day immersion in magnesium chloride solution. So such increment of the mechanical properties may be attributed to the further hydration of cementitious materials in both control and high volume fly ash samples during the immersion period. And we are going to move on to the gas permeability. So we cut the top and the bottom slice from the mortar cylindrical samples and put them in such device to measure the weight change. And then we can calculate the corresponding gas permeability coefficient of control and high volume fly ash samples. They both have a reduction of approximately 66% after 56 days immersion. So far we may find that the immersion in magnesium chloride solution under room temperature have some positive effects on the mechanical properties and durability of mortar samples. So we further conducted the X-ray diffraction analysis on the white precipitate on the surface of control sample. As you can see here, after 14-day immersion, we may find two main crystalline phase in the white precipitate, while after 56-day immersion, there's only one crystalline phase remaining in the white precipitate on the surface of control samples, which is magnesium hydroxide. So we can do some little formula transformation for the first disappearing phase, and we may easily find it is the magnesium oxychloride phase 3, also known as 318 phase. So the 318 magnesium oxychloride phase can dissolve in water or solution to produce the magnesium hydroxide and chloride ions. We can easily find that the magnesium and hydroxide ions can react and form the precipitation of magnesium hydroxide. So the solubility of the 318 magnesium oxychloride phase is mainly dependent on the concentration of magnesium chloride. When the value is lower than 1.5 mole per kilogram, the magnesium hydroxide phase will be the stable one. If the value is higher than 1.5 mole per kilogram, then the phase 318 will be the stable one. If you remember that the concentration of magnesium chloride solution in our study is 11% by weight, which equals 1.3 mole kilogram. That explains why the magnesium oxychloride phase 3 will disappear and finally converted to magnesium hydroxide. So here's the result of XRD and results of white precipitate on the high volume fly ash samples. As you can see, even after 56-day immersion, there are still two crystalline phases in the white precipitate. We still do some little formula transformation, and we find that the phase can be identified as magnesium oxychloride phase 5, also known as 518, which is different from that we found on the surface of concrete control samples. So you may think that, okay, the phase 5 is more stable than phase 3 according to the result of XRD, but actually it is metastable and it can gradually transform to 318 phase when the concentration of hydroxide of the solution decreases, and eventually it will convert to magnesium hydroxide. So we'll move on to the TGA results of the white precipitate on the surface of control samples and the hydration products from the surface of the control samples. As you can see here, the peak of calcium hydroxide is shrinking with respect to the time of immersion, and correspondingly, the peak of magnesium hydroxide and the peak of fetal salt is getting enlarged over time. On the other hand, the peak of the hydration products, which can be characterized as aggregate and CSH, is getting increased with the immersion time. Since the MSH phase does not provide any cementation function in concrete, we can confidently say that the main increment attributed to the formation of aggregate or CSH. For the TGA curve on the left-hand side, we may find that there are multiple shoulders for the peak between 100 and 200 degrees Celsius. That's because the phase 3 magnesium oxychloride phase is losing its water molecules gradually during the heating process of the TGA test. So here's the TGA results of the white precipitate on the surface of high volume flash sample and the hydration products from the surface of high volume flash samples. Similarly, we can find that the peak of calcium hydroxide is fully disappeared after 56-day immersion, and the peak of fetal salt and magnesium hydroxide is kind of overlapping and merging to a large wide peak. And the phase 5, the TGA of phase 5 magnesium oxychloride phase also shows multiple peaks, which indicating it's gradually losing its water molecules during the heating process of TGA test. So now I'm going to show you some SEM pictures of the control sample at the depth of 2 millimeter to the exposed surface after 14-day exposure. Based on the results of the EDX point data, we can identify some phases in this picture, like the unhydrated cement grains, which is the C2S, and the unhydrated cement grain identified as C4AF, or some hydration products of calcium hydroxide. As you can see, this is the phase of quartz with a bright and smooth surface, which indicates it's the fine aggregate. However, there are some dim and unsmooth surface on the surface of some phase on the surface of the quartz, which, based on the results of EDS point data, it can be identified as magnesium-rich phase, which means that the magnesium-rich phase can precipitate on the surface of the fine aggregate and cause some micro-cracking here. If I can show you here. And with the help of EDS elemental mapping, we can find the chloride-rich area, and we enlarge it. We can find some unhydrated C4AF phase, and with the hydration product AFM around it, and the layer-like structure of morphology of the fetal salt. So here's another SEM picture of the control samples after 56 days immersion at the same depth. As you can see, there are a lot of black holes, which means a lot more voids, which is caused by the calcium leaching. And again, with the help of EDS elemental mapping, we can find the chloride-rich area and enlarge it. We can find the layer fetal salt with layer-like morphology. Here's the SEM picture of the high volume flash sample after 14-day immersion at the depth of 2 millimeters. We can identify the unhydrated cement grains C3A and C4AF, and also the phase of quartz from the fine aggregate and flash, respectively. Also, we need to find the chloride-rich area. We can see the layer-like morphology of the fetal salt along with the AFM, and this is the CASH that we can identify based on the EDS point data. So similarly, we can find that after 56 days immersion, there are more black holes, indicating that more voids, which is also caused by the calcium leaching. And we find the calcium-rich area. Also can see the fetal salt with layer-like morphology. So I'm now going to make some conclusions. The first one is that short-term immersion in magnesium chloride solution under room temperature can have some positive effects on mechanical properties and durability of ordinary Portland cement and high-volume flash concrete by facilitating the further hydration of cementitious materials. The second conclusion is that the 318 phase and 518 phase of magnesium oxychloride can precipitate on the surface of OPC and high volume flash samples surface respectively, but they are both metastable and will convert to brucite eventually, which is the magnesium hydroxide. And the last one is that the brucite phase or some magnesium-rich phase can precipitate on the surface of fine aggregate and thus cause some microcracking at the interfacial transition zone. And the fetal salt shows the layer-like morphology. The calcium leaching can generate more voids over the immersion time, and I believe that in the long term, it will cause severe deterioration. So here's my contact information. If you have any questions, just feel free to ask me or email me. And once again, I would like to acknowledge the financial support from AAA and the assistance from my undergraduate research assistant. Thank you.